Send some videos to Becca saying that it's and now I like send him buttons. Well,
It's been busy, but it's good. Yeah, how about you?
Yeah.
Do you enjoy it?
And if he doesn't, then
Yeah.
Okay, good. It's always good that it falls within that. Oh, okay. Okay. I think everything, under the studio thing, under live, it says no signal. Do I have to worry about that? Should I be able to see it? Because you had OBS. Oh, I see.
All right, everybody. Good morning. It is my pleasure to introduce today's special seminar speaker, Becca Mangini-Hall. Becca comes from the mountains of Northern Virginia. She got her bachelor's from UVA, Physics and Environmental Sciences. And roughly 2 years ago, she joined a research group here at the University of Wisconsin. And she's been working on the thermodynamics of mesoscale convective systems in the tropics specifically. And she's been a great part of our group. So without any further ado, take it away, Becca.
Yeah, alright, so thank you for joining me this morning. I'm going to be going over some of the work behind my master's thesis, looking into an analysis of the thermodynamics and dynamics of tropical mesoscale convective systems. So, right off the bat, I just want to quickly define what we mean when we say mesoscale convective systems, or MCSs. So broadly, they're defined as a system of thunderstorms that is larger than a single thunderstorm cell, as you can see on the left, but smaller than an extratropical cyclone, which you can see on the right, which takes up nearly the entire continent of North America. So, no, yeah, those are the ones we're looking at. It's important to note that these storms do occur globally, and they're actually strongest in the mid-latitudes. However, due to their spatial domain and impacts, they are very important in the tropics as well, where they actually contribute to 93% of the annual tropical precipitation. And this is one reason why our research is going to be focused on the tropics as our spatial domain. And when I say tropics, I mean the band from 30 degrees south to 30 degrees north. I'm also in the large-scale tropical dynamics group, so it'd be really weird if I wasn't looking at the tropics. So, yeah. Looking into some of the impacts, this research is really important for a number of reasons. One of them being is that MCSs act to redistribute mass and energy throughout the entire atmosphere, with many of these systems making up the rising portion of the habitacell over the equator, where they take energy and mass and transport it up into the atmosphere, where mass, the water, condenses and precipitates out, where the tropopause then acts as a ceiling, causing mass and energy that is up there to move forward before redescending into the descending branch of the habitacell, and then interacting with the nearby ferrocells, or polar cells if you're a ferrocell either, and then combine back to the surface as the treatments. Obviously, there's also a humanitarian motivation behind this. MCSs can have really devastating impacts in terms of lightning, landslides, flooding. You can see here some pictures of just some of the devastating impacts that these storms can wreak on communities in the tropics. And it's especially important when you consider that 40% of Earth's population was active in the tropics. So that's a really big portion of people. And if you're thinking like that's great for the people in the tropics, how does this actually like impact me? Well, in a warming climate, we're expecting to see storm intensities to increase. So the better that we can understand and prepare for these systems in the tropics, the better we can understand and prepare for them in the future with the warming climate. I think Bill Nye puts it really succinctly. The planet is kind of on fire. So now I just want to go into some of the things we do know about mesoscale convection systems. And one of those things is the way in which we define and establish the MCS life cycle. So first, as you can see in this really beautiful figure, in the first stage we have the formation or growth of these storms, where you're first seeing the initiation of convection occurring. Stage 2 is when maturity is reached, and this is the point at which you reach maximum precipitation rates. And then lastly, you have the decay phase, where the system is no longer emitting new convection and it is precipitating out in the form as the stratiform deck and the remaining anvil behind. So some more of our current knowledge. We know that high buoyancy and high boundary layer moisture are associated with higher probabilities of MCS occurrence. And this makes intuitive sense, like the more points you have, the more it's going to rise, the more water you have in the atmosphere, the more water that you can have to precipitate out. Same idea where you have lots of high water vapor, you also see MCSs with larger, broad stratiform regions. And a new, more recent idea with MCSs is the importance of the presence of mixing. And these can significantly impact MCS stability and strength and structure. And when I say mixing, I think I have a figure here from Sharon Nealon, 2019, where they show how mixing with the environment, so bringing in outside air that's not in the system, bringing it in and mixing it with the convective core in the center. So you're acting to dilute what's inside the cloud, inside of the system with outside air. Some of the things we don't know, we still have questions in how the thermodynamics impact the occurrence and characteristics of these storms. And then even more specifically, we don't really know how moisture, buoyancy, and vorticity come together to impact MCS clouds and their life cycles. So all this leads to the main research question, which is, how does buoyancy and moisture affect isolated tropical MCSs throughout their life cycles? To address this research question, we formed two main hypotheses. The first based on the historical focus of convection in the tropics, which was first conceived in a paper by Rill and Malkus in 1958, where they discussed the idea of an undiluted parcel acting as a hot tower in the tropics to transfer mass and energy to the top of the atmosphere. And with that, we believe in the hypothesis, the more moisture we're going to see, the more broad stratiform decks and the more precipitation we're going to see. The other hypothesis is more of a contemporary viewpoint, where we will be instead looking into the structure and evolution impacts caused by entrainment in the dilution. So entrainment, that's the act of bringing in outside air, mixing it in that iron, and mixed out. And dilution is just taking that outside air and mixing it with the air already in the system, acting to dilute its nature. So to test these hypotheses, we formed some data methods where we use two main data sources, IMERG, which is an observational product, and it has a temporal resolution of every 30 minutes and a spatial resolution of 0.1 degrees latitude by 0.1 degrees longitude. To facilitate easier comparison to our other data set, and then to also just make it more computationally efficient, this data was regridded to a 0.5 degree latitude by 0.5 degree longitude grid. The other main data source was AIR5, which is a reanalysis product, which for those who don't know, reanalysis product is you take observations and you fill in the gaps with model outputs. And the temporal resolution of AIR5 is every 6 hours, and its spatial resolution is 0.5 degrees latitude by 0.5 degrees longitude. So once we had our data, our next question was, how do we actually track these systems? How do we find out where they are in space and time in order to follow their evolution? Our answer to that was to use the tracked IMERG mesoscale precipitation systems, a tracking database created by James Russell at the University of Utah. It's called TIMPS, and so I'll be referring to it for the rest of the presentation. It has a spatial domain from 25 degrees south to 25 degrees north, and we used a temporal range of 2014 to 2016. We rationalized this really short time span since after filtering was taken account for, we still had about 100,000 storms per year, so I meant 300,000 storms in total, and with such a large distribution, we were able to continue on and be able to produce some bulk statistics in those only 10 years of data being considered. And then lastly, they define life cycle stages of the MCSs by their storm area and their volumetric rain rate. Where volumetric rain rate is just the integrated precipitation atmospheric column. At the bottom here, you can see a small figure showing how TIMPS identifies and breaks up storm systems in the tropics. So they used a tracking algorithm called the forwarded time algorithm by Gregor Scott at the University of Pennsylvania, where this is novel from other research because this is breaking down the storm into its component convective cores. So as you can see, if you were to treat this entire system as just one blob and you're trying to perform statistics on this thing, you would have significantly different results than if you separate this into the convective cores themselves and you actually analyze each of those as separate entities within the system.
So just quickly, what are the criteria for storm area and volumetric rain rate that tell you what stage it's at? How does that work? Or are you going to go over that?
I don't include it, but I can quickly say it's so they define stage 2, that's the maximum, as the maximum point of precipitation in the system, and then any time step after the maximum precipitation point that has precipitation rates that are less than 0.75 of that maximum, those are identified as decay stages, and then beforehand, ones that are below the 0.75 of the maximum are identified as growth stages.
Okay, and that rain rate is the volumetric rain rate?
Yes, yeah. So again, I just want to briefly touch back on the MCS life cycle, and in that definition, in the formation stage, that's where you're seeing the storm area and volumetric rain rate are growing. They taper off and are stable during maturity, and then begin to decrease in size and intensity in the phase. So our next step, once we had our tracking data set, was creating storm-centered composites so we can actually analyze some of the environmental conditions. So first, we used storm centers, which we defined as rain-weighted centers of the storms that we obtained from TIMPS. And this is referenced as a 0 degrees latitude, 0 degrees longitude within a grid box that we place around them. This grid box is a 10 degree by 10 degree box, and this entire square is what we define as a storm-centered composite in this research. Next, we filtered out MCSs that had a grid average vorticity larger than 10 to the negative 4 seconds. And this was just to reduce the impacts that tropical cyclones would have on this, as those have different structure, different mechanics. We wanted to focus solely on convective cores and MCSs. Next, we then further filtered and identified and used only the first instance of each storm occurrence in TIMPS within each stage. This was to reduce the impact of systems that may have stayed in one stage longer than another stage, or longer compared to other systems. And then lastly, we averaged our data using Area 5 and IMERG at the grid coordinates of the source area composites.
Second. Can I ask a quick question? Do you have any lifetime constraints on it? Does it have to exist for a certain amount of time?
When I emailed and asked them that, they said that that's coming out in a paper that's coming out soon.
So you don't have any filtered. So you use the different IDs, and it didn't matter how long it lasted.
Yeah.
Okay. I just wanted to check. Thank you.
Yeah.
Yep.
So the first part of my results, I'm going to go over some of the thermodynamic controls of MCSs. So first, here I have a figure, and the color contours are storm initiation density. So I took a point where each storm was first recorded in TIMPS and put it on here as a density heat map. The green contour lines you can see are total column water vapor. And so what's really important about this figure is that you can see an overlap between the storm initiation density and then the total column water present. You can see that as the density in storms increases, there's a very clear associated pattern of an increase in total column water vapor. This is acting to confirm that TIMPS actually is capturing these key processes, and it means that moving forward, we're going to be able to use tropics-wide bulk statistics instead of having to break it down by domain at certain latitudes and longitudes. Some areas of interest that I think are important to pick out. On the left in the red circle, we have the intertropical convergence zone, the ITCZ, where we saw total column water vapor above 48 kilograms per meter squared. And then over the Amazon basin in South America in our blue circle, which also saw total column water vapors above 48 kilograms per meter second. And then in the western Pacific warm pole, all the way on the right in our purple circle, where we saw the highest amounts of total column water vapor within the tropics at above 54 kilograms per meter squared. So now I'm going to go into some of the thermodynamics that we use typically in mid-latitudes to determine storm strength and intensity. The first one is convective inhibition, which you can see here. And this is a variable that allows us to determine how much resistance to upward movement there is in an atmospheric column. And so you can see here, we plotted out the mean distributions of these storms for each of the stages. They're all unimodal, and the changes are really subtle, but there you do see a slight shift to SIN being more positive anomalies as you increase the life cycle. So stage 1, the average is somewhere around 0. Stage 2 is a little bit higher. Stage 3 is even a little bit more. On the other hand, we have also convective available potential energy, which is the opposite of SIN, and this is how much inherent buoyancy a parcel holds so that it can transport up in the atmosphere. So in stage 1, obviously, when we're expecting most of our initial growth, we see the highest rates of convective available potential energy. Stage 2, when we're still having active convection happening, it's still elevated. And then as you can see in stage 3, once decay is started, Cape completely begins to drop off. Next, I also have total column water vapor. As you can see, there's really not a ton of differences between the different stages. They're all unimodal. They have same ranges, and their means are roughly around the same. And I think this is just important to point out that in the tropics, it is just so hot and wet everywhere that the total column water vapor really isn't varying that much, even during the different stages of the storm's life cycle. And then lastly, we have precipitation. This also, you can see that it's a pretty hard skew to the right, where most of the precipitation is being seen in stage 2, which is defined as the maximum precipitation point, and then stage 3, when you're having that stratiform right now of the remnant of the anvil. Here we have a top-down view of these horizontal storm composites for total column water vapor, Cape, and SIN, where the storm center mean is that 0.0 degrees latitude longitude I mentioned earlier. And you can see that we have it for stage 1, stage 2, and stage 3. So looking at total column water vapor at the top and then SIN here at the bottom, they have really similar spatial patterns and evolutions. They don't really change sign much between the stages at any major points. There's small fluctuations in their centers and the intensity, but they're not very large. But this completely contrasts though when you look at the Cape, where you can see a strong positive in stage 1 that then flips to a negative in stage 3. This is just confirming that there is indeed some sort of decline in the amount of buoyancy available as you go along in the storm's life cycle, where your Cape is going to be largest in the beginning when you're seeing most of the initial convective growth. This also just aligns with the aerial mean distributions on the previous slide, just actually confirm that this is what we're seeing in these thermodynamic variables.
Why do you think the SIN is larger
just from like mixing with the environment, I think, because when you have like the global storm, that's where you're having most of the instability, and I was thinking that's just where you're having like most resistance. I mean, it's really, really small too, if you look at the sun anomalies. And these are also lifetime anomalies, so it's in reference to the whole lifetime. So it's already very low, and it's just that fluctuations are small.
Are those are negative in the reverse? Okay.
These
so
are anomalies.
So it's lower. Oh, okay. Sorry, I got confused about the color scale.
Oh.
So it's lower in the
Yes.
center of the storm. That makes more sense to me.
Yeah.
Yeah.
This has a question.
Yeah.
Perhaps I missed it. Are these scaled by the size of the storm in any way? Or are these just like, little storms, big storms all mixed together?
These are all mixed together. Yeah. So it's 10 degrees latitude, 10 degrees longitude box around each storm. The next part of my results I want to go over some of the kinematics and structure, seeing if the Mesoscale convective systems. So the first thing we have here is omega anomalies. Before I continue to explain anything, omega, I will be referring to it as minus omega for the presentation, where the more positive this variable is, the more upward motion you have, the more negatives, the more downward motion you have. Just to keep it simple presentation. So as you can see, that omega reverses aloft in stage 3, and this makes sense, right? You're going to have most of your downward movement without precipitating out, and any of the remnant convection and upward movement is left within the stratiform deck. That is a aloft. And then in stage 1, you can see that there's divergence occurring in the middle free troposphere, in this middle one here, 500 pascals. And then you have convergence aloft, so at 200 pascals. And then if you look at stage 3, there's a complete reversal in this. So we are seeing that there is some sort of relationship between the point in which a storm is in its life cycle and then the amount of upward movement and redistribution of mass and energy curves. Another point I would like to single out really quick is that if you look here, you'll notice that the most upward movement is occurring in the middle free troposphere, so 500 pascals, in the second stage of the storm life cycle. So that's just something important to keep in mind for later. Here I'm looking at a vertical cross-section of the same omega anomalies. Now we have wind bars with the vertical winds included as well. For stage 1, stage 2, and stage 3. Again, red, upward movement, blue, downward movement. And this aligns with our horizontal perspective on the previous slide, and it looks a little bit more into some of the details present that you can't really see in just the horizontal cross sections. Here you can see where stage 1 and stage 3 have their reversals, but they occur in different parts of the atmosphere. So in stage 1, you're seeing this reversal around 600 hectopascals, and then in stage 3, you're seeing this closer to around 500 hectopascals. And so this is important to note that we are seeing inversions at different levels, and that stage 3 is at a higher point in the atmosphere at a lower pressure than stage 1 is. And then again, as I mentioned previously, the most upward movement we're seeing is in the middle free troposphere of the second stage of the storms, and you can also see that here where that's the greatest amount of omega anomalies. A quick aside note I want to make before continuing on with the analysis of kinematics and structure is some of the issues we ran into with the reanalysis data, the AR5 data. So on the x-axis, you can see the IMERG observational precipitation rates, and then on the y-axis, you see the AR5's precipitation rate. So for each storm, I got the rain rates from IMERG and AR5 and plotted it down here in a heat map distribution. The pink line is a 1-to-1 line, and that's what you're hoping you would see, that AR5 is accurately capturing the same amount of rain rates that the observations are showing. Whereas the black line is the actual line of best fit. As you can see here, AR5, it seems overestimates precipitation rates. And you can see that there's like a general relationship in stage 1 and stage 2. There's a slight positive linear relationship that's noticeable, but this completely falls apart when you look at stage 3 and the decay. There's no really discernible pattern, and there's a lot of variation present. So now, looking at the precipitation rates from Area 5 to the column integrated omega, we wanted to look and see if there was any relationships between the amount of upward movement and then the actual precipitation that you see in these storms during different stages. Again, stage 1 and stage 2, you can see a very clear relationship that's positively linear, where the more rain you have, the higher the column integrated omega is, minus omega is. And then once you hit stage 3, again, this pattern completely falls off and you just end up with a lot of noise and variation present. There's no really discernible pattern from stage 3. And we think that this is important to know in terms of Area 5 having difficulties in defining and capturing convective decay, which is another point I'll be going over later. So now, moving from precipitation to omega, I want to look more into the thermodynamic variables in relation to omega. So here we have temperature anomalies, red, warmer, cold, bluer for stages 1, 2, and 3. Black contour lines, the solid ones are positive omega, the dotted ones are negative omega, and again, this is minus omega, so positive upward, negative downward. So looking here, you can see that there are strong surface anomalies that are being capped near the surface in stages 1 and stages 2. Where you can see a noticeable decline in temperature maxes in stage 1 and then temperature minimums in stage 3. And it's around 900 hectopascals, and it's at the same level for both stages. From there, you can see above them and near like 650 hectopascals, there's another local maxima and minima for temperature in these cross sections. And these are important to note because we see that there's this separation occurring in the atmosphere. So there's something acting to restrain the movement of energy through the atmospheric column. And when you compare that with the specific humidity anomalies, again, omega is the same as in the previous one, you can see that there is very moist air at the surface, and this aligns with the warm temperature anomalies we see in stage 1 at the bottom. And then there's warm, dry air aloft. And so this is acting to cap and restrain further upward motions. You need enough energy in these systems for it to be able to break through this ceiling, and in stage 1, we're just not quite there yet. In stage 3, you see the opposite of this, with an almost floor nature of the convection in its decay, where you're seeing a reversal in stage 3, where you're going from cool dry air at the surface to cool moist air aloft. And I think this is just really emphasizing that at this point there is no active convection really occurring at the surface, and it is mostly just the stratiform precipitation. And then looking at the omega anomalies, the black contour lines, these also align with that, where you can see that upward motion is stopped once it reaches this warm dry point in the atmosphere in stage 1, and then your positive motion isn't until all the way at the top of the atmospheric column in stage 3, and that's where you're going to have the stratiform effect, and that's why you have upward movement there, but then the rest of the column is downward. This is the last main result I want to go over before discussions, and that's plume buoyancy. So, plume buoyancy can mean a lot of different things to different people, and for us, it's broadly defined as a stream of upward movement flowing away from its source. So if you look at the videos on the right here, at the bottom you can see how there are these rising columns in the cloud. And the figure on the top, this is actually a video I took from our building, and you can see the Convective towers building. there's like one, there's one, and you can see how in a real storm, the one at the bottom is an isolated one, but in a real storm you're going to have multiple of these cores going together and evolving. I think it's important when we think of like storms. I feel like people often think that the clouds are what's like modulating and controlling this storm system, when really clouds are just an expression of the plume buoyancy and the underlying mechanics that are happening. So clouds aren't driving it; it's the plume buoyancy and other factors that are actually driving it. We see this strong upward currents within tropical convective cores that make up and drive MCSs. So unlike in the mid-latitudes where you can treat these cores as isolated parcels, you can't really do that in the tropics. And this is a result of the weak temperature gradients in the tropics. Everything everywhere is hot and moist, so it's really hard to get any sort of development when your mean state is already so enhanced. So with that in mind, that means that the traditional thermodynamic qualities that we can use, such as cave and sin, to describe a storm's intensity, like we can in mid-latitudes, kind of falls apart once we're in the tropics. So, and that's where mixing starts to become really influential and is a really important part to consider in terms of the development of the plume. And in that mixing and then the unmixing components, that's how we're going to separate buoyancy. By the dilute, that's the part that's mixing with the environment, and then the undilute, which is the inherent column itself before mixing occurs. And we're going to have to consider both of these when we think of buoyancy as a whole. So the next issue was finding ways to quantify buoyancy. Traditionally, buoyancy really can't be straight, just measured like observationally in the atmosphere. In the mid-latitudes, often there are proxies used like equivalent potential temperature or CAPE to identify the amount of potential energy a storm has. But again, that falls apart once we're in the tropics. So here on a paper by et al. 2021, we see buoyancy quantified as the dilute and undilute components. So this is the equation describing the dilute component, the mixing, and then this is the part that's the undilute. So this is the inherent column, it's the inherent convection, the core itself. And again, to get an overarching look at buoyancy's nature as a whole for these systems, we're going to add these two together because we're considering these experts.
And can you remind us what the subscripts mean?
Yeah. So MSE is moist static energy. The subscripts B, that's the boundary layer. We define that as 1,000 hectopascals to 850, and then the L is the lower mid-troposphere, and that's 850 to 600 hectopascals. Yeah. For those unfamiliar with the notation, apostrophes are anomalies, and then asterisks are saturation. So MSE with an asterisk is saturated MSE versus MSE without it. It's just MSE. Yeah.
And so the top one is more like CAPE, and the bottom one, is that right?
No, the bottom one's more like CAPE, but that's where that's the inherent plume itself, and that's the undilute portion. And that's without considering mixing. The top one is where you are considering mixing occurring. So where it's where CAPE falls apart, like you can't use it.
Don't you mix in MSE and?
Yeah, you do in the system. Yeah.
Are you sure? I think you might have them switched.
Well, that is something I'll have to check.
They're both listed as BL there. They both have the same notation on the left-hand side.
Yeah. So that's why when you say they're describing buoyancy, it's just you have to consider both dilution and undilution in the system. Here, once we were able to quantify it for our storm systems and our storm composites, I plotted them here, where at the top, that's the entire plume buoyancy, that's both parts added together, and then in the middle is the undilute component, the unmixed part, and then the dilute, the mixed part. For stages 1, stages 2, and stages 3, where red is more buoyant, blue is less buoyant. And as you can see in stage 1, the plume buoyancy is really being dominated by this undilute component. For the inherent convective core itself is really important in dictating how much buoyancy and upward movement we're actually seeing in the systems. And that's converse to what we see in stage 3, where the dilute component and mixing with the environment starts to really become an important factor in the amounts, or in stage 3's case, lack of upward movement and potential energy via buoyancy. So with all my results pulled out, we went over the thermodynamics, the kinematics and structure, and then how these all apply in the terms of buoyancy. I'm now going to go over some summaries and some conclusions of the main points of this research. The first is that idea of convection that we are seeing in stage 1, where temperature and specific humidity inversions around 750 hectopascals act to restrain buoyant motions. The temperature figure back again, where you can see at 750-ish, that's when you're seeing the second maximum start to arise in temperature. And this is the point at which you're seeing that warm, dry air that's constraining the further upward development of the convective flames. Mass and energy are unable to dissipate, and so they start building underneath of this cap. And that's actually what we need in order to have a storm. Otherwise, the mean state, these would just be dissipating, and you wouldn't have enough energy built up to actually break through this capping barrier. But with the capping barrier present, you're able to slowly grow this potential energy near the surface until the point that it can break through the boundary layer up into the further up in the atmosphere. But you can see in the cumulus mediocre clouds, the ones up top, that's where you would see this happen. The storms aren't able to really see that strong convective growth required for a storm, like the congested CP this yet. So, yeah. And then when we consider also the omega profiles, these also confirm that upward motion is halting near 700 hectopascals, which is what we define as within the troposphere. Again, bringing back that figure, the solid lines are upward movement, dotted lines are downward movement, and you can see very clearly that there is some sort of mechanism stopping upward motion in the troposphere. The second main point I want to go over is the relationships we saw between precipitation, omega, and buoyancy. Looking specifically into how connections between precipitation rates and omega act versus how we actually observationally see that buoyancy maximums are being observed in stage 1. So this is suggesting that there's delays occurring between the max buoyancy and the max upward motion precipitation rates that we're seeing. They're temporally displaced from one another, where you're seeing the most buoyancy occurring in stage 1. However, the most upward movement we're seeing is actually happening in stage 2 during maximum precipitation. And this is an important point in reference to considering how buoyancy as a potential energy is related to the actual upward motion, the actual kinematic energy being expressed. And I think that's a sort of unintuitive point. I feel like most people think the more buoyancy you have, the more upward motion you're going to have at the same time. But we're seeing that that's not really the case here. And to summarize that idea, I brought up the MCS life cycle once again. So, stage 1, during formation, buoyancy is at its max, but vertical motion is weak. In stage 2, buoyancy is still positive, however it's decreasing, and the vertical motion at this point has reached its max, and then decay will begin to decline. My last main point is looking into issues in capturing some storm decay. So we're seeing disagreements between ERA 5 and IMERG data looking at precipitation, where we're seeing that IMERG, that's the observations, that's what we expect to see is working, versus ERA 5, which is the reanalysis product, really isn't showing this precipitation, especially in terms of the UK system, the UK stage of the MCS life cycle. Reasons for this is potentially that stratiform growth and structure is still under active investigation. We don't fully understand how the mechanics behind distort the structure. So then that makes modeling it more difficult. And then yeah, capturing and modeling significant changes is difficult. And that can act to influence the air five, and that's why the reanalysis may be so different from the observations. Another way that we see this issue in capturing storm decay comes in the form of like how we define storm decay. So if for each tracking data set you're looking at, they're going to have different definitions for what decay looks like in a storm life cycle. TIMPS' definition is that it's a time step after the lifetime precipitation max with mean precipitation rates lower than 75% of that maximum. And so this has just implications in previously how we were trying to understand the precipitation and omega relationships in stage 3, and just without with all the issues with the precipitation in air 5, we really can't understand that relationship that well right now. I also wanted to show you just an example of, in terms of how we define a decay stage, that can be really tricky. So in the top one is an example that follows the TIMPS definition that actually works pretty well. You can clearly see that there is a growth phase, it reaches maturity, and then subsequently decays.
Sorry, what are the lines?
So
It's
the
time and the two lines, what are the two lines?
yeah, so the dotted line is the area, I believe, and then the hard line is the precipitation.
Okay, so there's no access for the area listing.
Yeah, sorry, these are from different.
Yeah, it's double axis plot.
Yeah,
It's got
sorry.
two axes and there's only one drop. Okay.
So they're next to each other, right?
Yes,
The left axis is the more top left and the
yes,
right axis.
Oh, I see.
Yes.
Okay.
yeah,
Now
sorry,
I
they
understand.
should be together. Yeah,
No, it's the same axis.
Yeah, they're-
Sorry. They're next to each other. Yeah, one of the axes isn't drawn on, is that right?
I mean, this was a figure that was like A, B, so they just have corresponding ones. I just broke it up so you could just see it a little bit easier.
But that's just one axis and it's area and
Yeah, volumetric rain rate for both.
volumetric rain rate. And
Yeah.
those are two different units.
Yeah,
And there's not two different units listed. Or there are. Oh,
yeah.
sorry to.
It's okay. I can show you later too.
They both have units of K. I see. But one of them is area and one of them is volumetric rain rate.
Yeah.
So they have the same unit. Oh, I see. They have different. Okay. They're the same one. Yeah. Sorry.
Yeah, so this was a good example. And then the one below is a more poor example. If you can see, there is a point between stage 2 and stage 3 where, according to TIMPS' definition, there is a part of the storm's life cycle that we can't even define in the storm's life cycle. We can't definitively say if that's a stage 1, if it's maturity, or if it's in the decay phase. And that's just because of differences that we have in the area observed and the volumetric rain rates that are being measured. And so I think that's just an important thing to consider when we're doing an analysis on these things, that results, especially in regards to storm decay, aren't fully reliable just yet, and that's just because we have a lot of questions on what exactly storm decay means and what it looks like. Yeah. So then, to go back, I want to readdress the main research question that was, how does buoyancy and moisture affect isolated tropical MCSs throughout their life cycles? To answer that, I made this little figure here where I tried to pull together most of my main results. The color contours, the blue, that means it's more moist. The brown, it is more dry. The green arrows are the horizontal winds, and the red arrows are the vertical winds. With all of this put together, I then went in and kind of drew out the type of cloud morphology that we expect to see with these present thermodynamic and dynamic structures. And you can also see here how we define the boundary layer versus the lower troposphere and then the upper troposphere above that. So in stage 1, you're seeing that warm, dry air aloft acting to cap further development of a cloud that is where it's warm and moist at the surface. And you're stuck with those cumulus mediocre clouds that are very shallow. You're not able to run not fully having like a full convective column that's reaching all the way up to the top of the atmosphere yet. Top of the troposphere. And then in stage 2, we see that this is where the max upward movement is actually occurring in the entire life cycle. And this makes sense. You're seeing the full cumulonimbus is fully developed at this point. That's when your cores are going to be at their strongest, and that's when you're going to see the maximum precipitation. In stage 3, you can see the relationship of the dry and cool air at the surface, but then the wet and cool air aloft. That is from the precipitation. I purposely left the bottom of stage 3's cloud a little vague, just because I think it really represents that we don't fully know exactly how the stratiform data is evolving during this stage. So me drawing in a cloud there just didn't feel right. I think it's important to note that there are just ambiguities there still. And then my last thing I want to go over are just some of the implications of this research and next steps. In order to establish further insight into what drives tropical and mesoscale convective systems, we want to next first begin analyzing the observational cloud data. Try to start digging into what type of morphologies we're seeing at the different stages and what different the thermodynamic and dynamic conditions are associated with the different clouds that can be observed. And then another area that we would like to explore is the comparison between continental and oceanic systems. This is, I think, an important next step because with these differences, over the land you're losing the moisture surface that the ocean serves. But this also means that there's more instability available. And I think this has important implications when we look into storm initiation and growth and what allows one cloud to actually develop into a storm and what would make another cloud decay and fizzle out and not develop into a system. And then lastly, I would like to really go and start analyzing the decay stage that we're seeing. Obviously, that's where we saw the most issues, especially in terms of the precipitation and the reanalysis. I would like to start by looking into some of the buoyancy effects that are present during this stage. And I think it's really valid to start thinking about how we actually define a storm life cycle in storm stages. I think there's merit in questioning the validity of having a set life cycle with hard time and spatial boundaries. The atmosphere in reality is very messy and has a lot of chaos and a lot of moving parts. So I think trying to use hard rules in setting what growth versus maturity versus decay isn't fully appropriate when we want to describe how a storm's evolving. Perhaps looking instead into how the tropics as a mean state are just exhibiting storms as expressions of differences in that mean state. That's all I have. I'd like to quickly thank my professor, Angel Alonso, for helping me with all of this work, and then of course my committee, Mrs. Angela Rowe and Ms. About. The entire large-scale tropical dynamics group. You guys have helped me so much with this research and listening to me complain about so many things. Grandma Rosa, I love you, and you're like the kindest person I've ever met, and you are so patient with me, and I really appreciate it. And then I would thank Grandpa Victor, except he'd rather be in Italy right now than here, so, yeah. And then I want to thank all my lovely friends I made in AOS and Madison. I really did not like the idea of moving to the Midwest, but you guys have changed my opinion on that. I like Midwest a lot more now. And then Darren and Carl, you guys came all the way to Wisconsin to listen to me talk about clouds for an hour, which really isn't all that different from what we normally do, but I don't feel bad about it right now. And then my roommates, you can see. And then lastly, I'd like to acknowledge my family, and then the awards that funded this project, the NDSEG and then NSF Award, 222. Lastly, I want to thank you all for coming for my presentation. And are there any questions?
All right, we have time for a couple questions.
your hand if you have a question. Alyssa, and then Mayra.
I have a couple questions, but I won't ask them all at once. So you showed, I'm wondering if you think that the vertical advection of moist static energy is playing a role in the growth of decay.
That's a really good question. Yeah. Sorry, I was waiting for that. Yeah, so I think it does, because then that's impacting the like evolution of the system, especially how like it changes the properties through the column as it is being transported and mixing.
Because you have bottom-heavy profiles ahead, and that would lead to the import of moist static energy.
Right. Yeah.
And then you have top-heavy profiles behind, and that would lead to the export of moist static energy.
Right. Right. And we're seeing that in like the terms of like the dilution of diluted components and like European buoyancy.
I didn't catch that part.
Here you can see that like, yeah, you're seeing more like of that advection occurring in stage 3. It's diluting the system. There's a stage 1.
Where can I see advection here?
So that's just in the diluted component. So the more diluted it is, the more advection we're seeing is occurring in the environment.
Okay, I didn't usually talk about that.
Okay. Yeah.
Mayra.
We also have a couple of questions, one on the frame myself. They're just general, I'm just curious about the research. The composites, are you using the entire tropics? And also what years are you taking into consideration?
Yeah, so we are using 25 degrees south to 25 degrees north as our domain. So all of the longitudes within that latitude belt. And then we're taking data from 2014, 2015, and 2016 during the entirety of all of those years.
2 more questions. General
Yep.
question, how is your research different compared to what we have learned about MCSs in the subtropics?
In the subtropics?
In the mid-latitudes?
Oh, mid-latitudes. Yeah, so that's where this idea of like there being this mean temperature gradient being present, and the mean state of the tropics just being so warm and moist that perturbations in it really aren't enough to set off storm growth like we see in the mid-latitudes. And then I think that's where like we really have to consider the impacts of mixing with the environment, just because that's not as big of an issue in the mid-latitudes. Like we're able to like somewhat accurately quantify like storm intensity just available based on what's available like surface information and from like sounding. Yeah.
And so the last one has to do with the cloud portion of it, and that's my remote sensing person in me. I was quite curious about how you did. So you talked about cirrus clouds and stratiform clouds, and of course you can get some information from that in reanalysis. But cirrus clouds in reanalysis, so whatever you get that's very thinly
Right.
related to moisture at those higher levels in the atmosphere in reanalysis may come with a lot of errors.
Yeah.
So I don't think I quite understood how you got the composite using the cirrus clouds in the stratiform, especially those 2 plots that you had before. And I'm a little curious, and I'm glad that you mentioned it at the end. How are you planning on implementing satellite observations to look at the stratiform and the cirrus in the future?
Yeah. So when I was saying in the decay stage, this is just based off of like the general structure of like storms, where like they say that as it's decaying, you're having like the remnants of the anvil, and that's like the cirrus and the stratiform deck. And that's why I actually do want to go in and start adding in the actual like observational cloud data that we're seeing to see like, are there differences between like cirrus? Are we seeing like more accurate things over like the stratiform area? How accurate is that stratiform area? Is that comparing to like observations we're seeing at the surface too? And how those all just relate to one another.
In case any students have any questions, I'll give them. In case any student questions? Before we move on to more questions? Give us that faculty president, Liz, Angela, and Larissa again.
Cool. I'll keep these 2 questions short. One is methodological, the other is more open-ended.
Okay.
So on this plot here, you've got storm centered from 5 degrees longitude, 5 degrees latitude. I'm curious, did you scale the longitude based on the latitude? Because a degree at longitude at 25 north is very different from a degree of longitude at the equator. And I don't think it's going to change the results very much, but it might change the details.
No, we didn't scale it. That would definitely be good with more time to be able to go in and be able to account for those differences. Yeah, because there are differences, right?
Yeah, and it might be a good idea, instead of
Yeah.
using degrees, longitude, and latitude, just use straight up distance, like 100 kilometers by 100 kilometers.
Yeah.
Because then you don't have to worry about that at all.
Yeah, absolutely, that's right.
And then my second question is, in the course of research, we go down a lot of different rabbit holes. I'm wondering, could you tell us about one of those rabbit holes, or did you do any types of decompositions yet? You mentioned you're going to do continent versus land, but did you do anything by like location, ITCZ versus different continents, different latitudes, small storms, large storms?
Yeah, so I think, well, no, one of the ones I wanted to go down that Anhel was like, no, you need to focus, was really just looking into like the decay phase, especially the vertical structure that we're seeing in the decay phase, and I think that is going to see like very large differences in different areas, and then also over like land versus ocean, because then you have to account for like differences in the type of air that's being entrained in at that point, and then also just the initial state of the rising plume as it first forms. And I think that there's going to be a lot of differences in there that would be really fun to kind of look at and see how those are either one influencing the evolution of the growth in stage one, or then are impacting then the decay afterwards.
Thanks.
Yeah. Angela?
I'd rather email them to you later to leave more time and space for student questions and comments, so I'll follow up with you later.
Okay, sounds good.
Your abstract mentioned quasi-equilibrium and moisture quasi-equilibrium. Where did you take that part out, or does that fit into this picture?
Yeah, so that was, we wanted to focus a little bit in this presentation. This was kind of decided after the fact. We wanted to focus mostly just on the thermodynamics, and just like the impacts from like temperature and like moisture that are present. In my written thesis, I do go into this a lot more on how, moisture, quasi-equilibrium, moist quasi-equilibrium kind of come into play with these. Yeah.
All right, we have time for one more question, especially any students that have questions.
I talk a lot, so they probably already are like, she talks too much.
All right. Any general last questions from the overall audience, general audience? All right. Well, thanks Becca for the presentation. Thank you all for coming, and continue to ask questions.
Nice job. So with the plot that you showed me there, you were like,